Welcome to this video that was taken from a session that was presented at SharkFest 2016. In this video, we're going to go ahead and record that session, and if you have any questions about what you see here, feel free to comment below. The title for this session is TCP Tips, Tricks, and Traces. Let's chat about what makes applications crawl. Before I get started into the content of this presentation, just want to introduce myself real quick. My name is Chris Greer, work for a company called Packet Pioneer LLC. I'm a network analyst and also a Wireshark certified network analyst. For Packet Pioneer, I provide training and professional services with Wireshark, also helping people to resolve network and application problems. So those weird things that slow down on networks and make us scratch our heads and wonder if it's the network, if it's the application, if it's the server, those are the types of things that I troubleshoot. You can keep in contact with me right here on my YouTube channel, or you can check out lovemytool.com. That's where a lot of network analysis tips and tricks are posted for several different vendors in the industry. Great site to check out if you haven't stopped by there. Also, you can get a hold of me at packetpioneer.com or feel free to comment below. So in this session, we're going to talk about why TCP is such an important thing we should discuss. Well, basically, TCP is used by important stuff on our network. Mission-critical applications use TCP to deliver sensitive data between clients and servers and then back in the other direction. Now, a lot of times when I'm out there troubleshooting or I'm teaching people, one question that I like to ask them, I like to ask IT organizations is, what's the oldest technology that you are using in your network? Now, sometimes that'll get a response from people like, 2005, I have a few drivers that are pretty old, or I have that one old printer that's been sitting in a corner for almost a decade now, or over a decade now. So clearly that's the oldest technology in my network. But you might be surprised to learn that TCP IP, these two protocols and some of the other underlying protocols, these protocols are aged, they're old. In fact, if we look at TCP, the RFC for TCP was originally written back in 1981. So think about that for a moment. The core protocol, TCP, which hasn't dramatically changed since then. There's been a few options added and a few tweaks that have happened that make it a bit more efficient. But it's a 35-year-old technology. So nowadays in 2016 and beyond, what we're starting to see is some of the weaknesses of TCP come to the surface. That's why some problems can hide at this layer of the OSI model, the transport layer, specifically TCP when we're talking about connection-oriented, reliable transmissions. And TCP is key, it's critical for us isolating the problem domain. But the problem with TCP and problem with the transport layer is that few people in IT organizations really take responsibility for it. Now, let me show you what I mean by that. When a network problem strikes, when something happens and performance is bad, if we take a look at the OSI model, we find that network engineers, if that's the silo within the IT organization that we're coming from, if we take a look at that OSI model, we're responsible for the lower layers. We're responsible for the physical layer, so the cables, the Wi-Fi environment. We're responsible for data link, for the switches, the Ethernet, the point-to-point part of the network. Also, the network layer. So making sure that data efficiently gets from point A to point B with low latency and low loss. That's our job as network administrators or network engineers. Now we might say that we also own just a piece of the transport layer by firewalls or by perhaps load balancers. Those also can tweak and muck with the transport layer settings, specifically with TCP. Now if you go to any HR department and you pull my job description, that's what you can hold me responsible for as a network engineer. So when that problem strikes, what do? I go to my network interfaces, I check utilization levels, I check link errors. I want to see, is the problem on the network or not? And one of the reasons why I'm quick to do that is because the network gets so much blame for problems today. If something's slow, if there's a delay, sure enough, people are going to blame the network. They're going to say the network is slow. Now, something that I've found interesting over the years, I'm sure you've found this as well, is that even non-technical people blame the network. Have you ever called into a call center, maybe to a credit card, or maybe you're changing a flight, and the person on the other end of the phone who's sitting in a call center non-technical from a network perspective, perhaps their system is running slow. What do they usually tell you? Typically they say, our network is slow today. And I always think that's a funny thing for them to say, because under the hood, it might be something that's completely different. It might be a server, it might be an application, it might be a service that's running slow. But really, even they are conditioned culturally to blame the network. That's why, as network engineers, we often go into defense mode. We want to cover ourselves. We want to prove it's not the network. We want to validate those lower 3 layers that we are absolutely responsible for. Now, if we come in from the other side of the IT house, we find that if we're a server, application, a virtualization, a system support person, when a problem strikes, we also check those error logs. We check server resources. We look at CPU. We look at memory. Try to see if we have a runaway process. We want to know if the issue is ours when a problem strikes. Now, a lot of times these people won't know that they're taking responsibility for those upper layers. A lot of times they don't use that OSI model in the same way we would as network people. But they are responsible for that session, presentation, application. We'll bundle those together and call those upper layers. They're responsible for the service that's running on that application. If they're an application developer, they're responsible for that code, the way that users interact, and how those queries come into that system. So when a problem strikes, they retreat to their system and try to figure out if the problem is theirs up there. Now, do you notice one layer of the OSI model that typically goes overlooked? Yes, the transport layer. What we find culturally today in a lot of IT departments, and this is something that I've found as both a consultant and a trainer traveling around the world and talking to people in these scenarios, in these environments, a lot of times when finger pointing goes from one to the other, a lot of times I find that people are fighting over either a problem that is in the transport layer or a problem that can be determined by analyzing what's going on at the transport layer. So what I'm not saying here is all problems are a result of the transport layer. That's not what I'm saying. But we can use the data found there, specifically TCP, and that's what we'll talk about in this session, to hone in and figure out, do we need to go up to the application or do we need to go down to the network to resolve what's going on? And that's what we're going to discuss today. So when you're capturing traffic with Wireshark, let's talk about what you should look for in those trace files. Now, Wireshark has some great error events to flag TCP problems. Now, if you're accustomed to applying and using display filters, a display filter that you absolutely want to keep in mind is tcp.analysis.flags. I'm going to show you that when we actually get into a trace file just in a second. If you use that filter, what that will do is it'll help you quickly spot the errors or the issues that Wireshark has found at that layer, at the transport layer, specifically with TCP. Or if we're using Wireshark 2.0 or above, we can take a look at the intelligent slide bar off to the right, and we can quickly see those events over there. So what types of events are flagged? What types of things will Wireshark point out for us, or will we be filtering for? Well, we'll see that filter that I just showed you. That'll show us TCP retransmissions. It'll show us out of orders. It'll show us dupacks. It'll show us zero windows, even window updates. Now, those are the big ones. There are some additional ones that'll be displayed for you, but these are the big ones that you want to try to find. Now, I'm going to show you why and show you how to set that when we're actually getting into Wireshark. So let's go ahead and bring that up. I'm just going to open up a trace file. It's a basic trace, and it shows us just a simple example of a user going out to a web server and getting an image. Okay, nothing super special here, but what we want to take a look at as far as TCP is concerned is the highlighted packet here. So first of all, if we come up to the top, we can see that a client is connecting to the server. It's sending a TCP SYN. So this is the first packet in the three-way handshake between client and server. And what we notice here is over here on our time columns, we can see that we wait over 3 seconds, and then the client sends a TCP retransmission. Now I'm going to talk about these two time columns for just a minute. Now, something you absolutely want to do with your copy of Wireshark, no questions asked, if you're using a default installation of Wireshark, you want to add a delta time column. Now, the difference between a time column and a delta time column, like you can see here, is that the time column shows us a running total of time from packet 1 all the way to the end of the trace file. What the delta time column will show us is the amount of time between those packets, or technically from the end of one packet to the end of the packet that we're clicked on right now. So that delta time column is an important one to add. Now to do that, to put it pretty simply, all you got to do is go up to the Edit dropdown, come down to Preferences, and then we want to go to Columns. Once we're in Columns, down here below we have the ability to add or delete a column. What we want to do is we want to add one, and I'm going to name this new column, double click on it, and I'm going to call it Delta. Then I'm going to come over here to the column type. This shows me the type of information that will be displayed in this column. So if I just left this alone and hit OK, I would have a new column called Delta, and it would show me the frame number. That's the information that would be displayed in that column. Now that's not useful for me. I want that to be up here under number, right? So that shows me the number of the frame. So what I'm going to do is hit this drop down, and we're going to scroll up to Delta time displayed. That's the one that we want to show. So when I've added the display filter and some of my packets are filtered out, what this is going to do is it's going to show me the delta time to the previous displayed packet rather than the previous captured packet. All right. Now from here, if I want to, I can drag this column up to make it close to the time column. That's something that I like to do in my copy of Wireshark. I'm going to delete this since I already have a delta column here. And then I'm going to hit OK. Now that's just a style thing. I prefer to have my time and delta right next to each other. All right. In fact, I'm just going to enlarge the font just a hair. Okay. So here we are. We've got our delta column now. And this is something that you can definitely follow me on. Now this TCP retransmission, clearly we see that this happened 3 seconds later. Now at the beginning of a TCP conversation, that's what we're going to see as far as our TCP retransmission timer. So the SYN was sent, we wait 3 seconds, we retransmit. Now right away, I can tell one of two things. Actually, I should say one of three things, my apologies. The first thing is I want to know, or I want to determine, did the network drop this packet, this first SYN? That's a possibility, that this SYN went out from the client to the server, and somewhere along that path, it got dropped. Another possibility is that this SYN made it to the server responded with a SYN-ACK, but that SYN-ACK got dropped. That's also a possibility. That's more unlikely. That's an unlikely scenario because then I'd probably see a faster retransmission from the server side, or at least I would see that SYN-ACK come in. But it's a possibility. So either the SYN got dropped, the SYN-ACK got dropped, or it's possible that this SYN made it to the server, but the server was so busy doing something else that it didn't respond to this SYN. Maybe it was congested, it had a lot of connections and clients that were doing different things, and it simply didn't have enough resources to support a new TCP connection. That's also a possibility. So what I'd want to do as a network administrator, since I'm responsible for the network, I see a TCP retransmission. That means that packets were either lost or the server could not respond. So again, since I'm a network person, my responsibility is to make sure that stuff's getting between clients and servers reliably. So what I'm going to want to do is I'm going to want to walk the path between client and server and take a look for things like FCS problems, congestion, discards. I want to see, is there anything between that client and server that is causing packet loss? Maybe I have a hardware issue. Maybe I have a faulty cable somewhere along there. Because that way I can, if it is due to packet loss, when we do see retransmissions, that's where we can really dig in and we can find what's happening on the network as far as packet drops. Now, ideally, as a consultant coming in, something that I like to see is I always try my best to get dual side captures. I want to capture from the client end and I want to capture from the server end simultaneously. Now, the nice thing about this is here we see a client-side capture. I'm going to show you in just a second how I know that. This is a client-side capture. I see it going off. It would be nice if I also had a capture on the server side to see whether this original SYN made it. And if this SYN does make it and the server doesn't respond, well, then I know that that's a congested server. Now, I said that this is a client-side capture. There's a couple quick ways that we can determine that. First of all, I have a private address here on the client side. It's 10.network and it's sending off this SYN. That's the first reason that I know. But also, if I come down here to my frame details, if I expand out the IP header information and I scroll down to the TTL. Now this TTL shows me that this packet has not been routed yet. This is what we call a full TTL. So TTLs will start at 255, 128, 64. There's a couple other ones, but those are the big three. 255, 128, and 64. So just by clicking down here, I can quickly see the time to live is full. That's either true or this TTL started at 255 and it was decremented 127 times already. So that's unlikely. Right? It's more likely that this packet simply hasn't crossed a router yet. If I captured this same exact packet on the other side of the first router, this TTL would have decremented down to 127. So that's how I know if I'm a hop away from the client or how many hops away from the server. Now on the other direction, if I take a look at that third packet down, that's my TCP SYNAC. I can see that in the details. The server is coming back 14 milliseconds later. If I come down to the time to live, the server, the packet from the server shows me 113 TTL. Now, I can pretty safely assume that this packet started, or when the IP values were originally set, this began at 128. So I know unless there's another device in the middle that's terminating this connection and starting up its own one, then I know that the server began this time to live at 128. I can make an educated guess. That server's 15 hops away. Okay, so that's how I can tell where in the packet stream I've captured. So since I'm capturing client side, this is something that I want to take a look at. I want to scan in, see how much of those hops do I actually control, or how much is a part of the domain that I'm a part of. And how can I get in there and really begin to troubleshoot and find that packet loss? Now you notice that in a trace file, when you have TCP issues like TCP retransmissions, those are flagged black and red. Okay, so Wireshark is trying to point this out to us. Like, hey, Mr. Analyst, this is bad. Look at this. Now, what can be helpful is when I'm taking a look at a trace file, I want to see all of those bad things displayed for me. Now this is a quick trace, it's only 11 packets, but imagine that it was 500,000 packets. I just want to see, do I have retransmissions or do I not have retransmissions? To quickly do that, what I recommend you do is let's add a button up on top that's called Bad TCP. Now what Bad TCP does is it adds the display filter tcp.analysis.flags. What that shows me are all TCP bad events that are happening in this trace file. So again, retransmissions, out of orders, dupacks. It's going to show me window updates. It's going to show me 0 windows. So stuff at the transport layer that I should know about. Now, this is something that I'll hit when someone sends me a trace file and says, hey, I got some issues. This is something that I hit right away. I'll just open up the trace, come up to Bad TCP, click, and then boom, I can see, are there network issues or not? Now, if in a TCP handshake I see low latency, I see low round trip times, and the bad TCP is clean, so I hit that button and nothing shows, right away in the back of my mind, I can pretty safely assume, okay, we don't have packet loss, we don't have retransmission issues. It looks like the network is doing its job and reliably and effectively delivering data between client and server. I'm not quite ready to let the network people go home, but we can safely assume that the network's not dropping anything. Now to add to add this button up to your bar up here, all we got to do is hit this little plus button right here, add a display filter button. Now when you hit that, right away you'll see that there's a label, apply this filter. So if I don't change that, that'll be the name that's given to me up there in that filter bar. So in this case, since we're going to add this button, just go ahead and name it bad TCP. And your filter is going to be tcp.analysis.flags. As soon as you hit OK, now bad TCP will be given to you. You can go up and click that, and without needing to type out that filter, it'll be applied to this trace. Now this is a nice feature to keep in mind when you're looking at trace files and you're looking at things that in Wireshark, especially issues that you continually come back to. If you're setting a display filter often for the same things, just turn it into a button. Like if you find like one for me over here, slow HTTP, one that I find that I'm commonly adding to trace files is http.time equals, or I'm sorry, is greater than 1. What that does is it shows me what this display filter will do is it'll show me all HTTP responses that were greater than 1 second or took longer than 1 second. That'll show me if I have some lagging HTTP, if I have some slow responses from application servers, and that'll help me take a look right at the application people rather than at the network. Okay, and that's also one that I've added to the top here with a button. Okay, so I'm just going to clear out my filter, and here we are. So that was just a brief overview of taking a look at a TCP retransmission. Okay, now let's take a look at another trace file, one that has some more interesting stuff in it. I'm just going to expand this out. Now you'll notice right away something I love about Wireshark 2.0 is the intelligent scroll bar. Now you can see over here in the intelligent scroll bar, what it shows us is this is from the beginning of the trace all the way to the end of the trace. And as I go over different parts of the trace that show different colors, you can see how I run over these black lines. Now those are my TCP analysis flags. That shows me where and when in a trace file do I have some issues. Okay, I'm just going to change this to my TCP plane profile. Okay, here we go. So if I come up to bad TCP, right away it shows me all of the bad TCP stuff that I have going on in this trace. Now instantly, without doing much more analysis, I can tell that I have some work to do on my network. I've got TCP previous segment not captured, I've got dupbacks, I've got fast retransmissions. If I scroll down here, I can see several more retransmissions. I've got out of orders. Now an out of order, let's talk about that for a minute. Basically what an out of order can be is either 2 segments were sent, imagine, this is just explanation of it, imagine that 2 segments were sent from the server and along the way they took a split route. And as they came out of that split route, they were reordered. Packet number 2 was first and packet number 1 was right behind it. Wireshark can show that as an out of order, like packet 2 beat packet 1 on the way to its destination. Or another possibility of an out of order is when I see, when I have a retransmission in the trace, but I don't see the original packet. Okay, that's another reason why we might see an out of order. In fact, what I'm going to do, I'm just going to right click on out of order, and I'm going to come down here to conversation filter. I'd like to show you how this looks with Wireshark. Okay, so I have a SYN/SYN-ACK standard TCP handshake. The client is connecting to the server. This client goes out and does a GET, and it says, hey, server, give me this stuff. This is the information that I want to see from you. Server comes back and says, all right, here you go. And then I start to see the responses come in. Well, along the way, notice what happens if I scroll down just a little bit here. Now here on packet 173, I can see TCP previous segment not captured. So I had the packet right before this one on its way back to me was not captured. Now that can mean one of a couple things. First, it could be that legitimately this packet was lost and this packet that I've collected was the one right after it. So I lost a packet up here. It's also possible that my copy of Wireshark simply didn't pick it up. Maybe I exceeded the capabilities of my span port, or maybe I hit the maximum capture potential of the laptop that I was using to capture, or something like that. Now, usually when you see DUPAX right after TCP previous segment not captured, I can rule out the one that I just mentioned. I know that right now my client is saying, hey, Mr. Server, I got this packet. I got 173, but I'm missing a packet above it. I'm missing some information. So it's likely that something you sent, Mr. Server, got lost, and I'm just acknowledging what I have seen. Okay, so now when you don't see DUPAX following TCP previous segment not captured, if you see this kind of randomly and it just flies by on your packet trace, typically it's not something to be terribly worried about. Usually it just means that this packet didn't make it to your analyzer, or the packet above, the one that's being flagged. The packet was real and it made it between the client and server and it was acknowledged, but we dismissed it because of where we were capturing. In fact, at SharkFest 2016, I was talking to a guy right after this session that I taught, and he told me, now it makes sense, all of those TCP previous segment not captured that he gets in his trace files. He mentioned that he often captures on one side of a split route. So he doesn't see the packets coming in on the other side. So this is something that he often sees, and now he better understood it. Okay, so let's see what happens if we scroll down further, coming down to the bottom of this messy little part of our trace. This is where I see a TCP out of order. Now what this means is that all these DUPAX made it to the server, and the server went, oh no, there's a lost packet. There's a packet missing. Tell you what, here's the replacement. And that replacement arrived out of order. See, Wireshark gets this packet and it says, you know what? I should have seen this up here. This should have come in up above 173. That's why we label it as an out of order. The reason why we don't label it as a retransmission, because technically that's what it is because we never saw the original packet. Now, if this same exact trace file was taken on the server side, what we would see is things going along just fine. We see packet, packet, ACK, packet, packet, ACK, packet, packet, ACK, and then all of a sudden we would start to see these DUPAX come in. Then we'd scratch our head and go, you know what? Wait a second, DUPAX, that's signaling that we had a packet loss. Let me examine this sequence and acknowledgement numbers, and let's go ahead and get that second packet out on the wire. This packet down here would be labeled as a retransmission, not as an out of order. And that's because we see the original packet in the trace. So for capturing, this is something, just a tip for you. If you're capturing client side or you see a lot of out of orders, that means you have upstream packet loss. Somewhere between you and the source of the data, in this case the server, somewhere between our capture point and that server is where that packet loss is happening. If I saw retransmissions, then I know that somewhere between my capture point and the receiver, in this case the client, somewhere between there I'm getting my packet loss. So it kind of helps you to first of all determine I'm getting packet loss, I'm seeing these retransmissions and out of orders, and second, based on which one they're labeled as, that'll help you determine what side of the analyzer to look for, either downstream or upstream. Okay, so that's just another tip as far as reading TCP in our trace files. Now there's quite a few other bad TCP events that we had in this trace file. So I'm just going to bring up bad TCP again, and I'd like to talk you through another one. We notice here, we already talked about TCP previous segment not captured. We talked about some dupbacks. Let's talk about window full for a minute. I'm going to go and right click this. I'm going to come down to conversation filter, and I'm going to come down to TCP. Now what this does is it sets a filter for the conversation of which this packet that I've clicked is a part of. Now some people go straight to like follow and TCP stream, and the stream data is exported out of that packet stream and it shows you on a separate window. For me, I don't really care about all that. I just want to quickly set a TCP filter. All right, so here we go. Here's another TCP conversation. And let's go ahead and take a look a little deeper of what's happening here. So we have our SYN, SYNAC, ACK. We have a GET. We have an acknowledgement. And then we have data coming in from the server. Now right away I can tell this is operating pretty decently. Things are looking good. I got a 10 millisecond round trip time between SYN and SYNAC. I'm fine with that. Looks good. If I take a look at the hop count of that packet coming back from the server, how many routing entities did we go through? It's likely this started at 64, so it could be 4, or maybe whatever is acting as a proxy, like a web proxy, could be answering that for us. So here's our get, here's our OK, and let's go ahead and take a look at that window full. Scroll down, coming down all the way to where are we at? So previous segment not captured. Looks like we have a missing packet. Looks like we're doing a dupeback. What this does is it advertises to the server which packet was lost. We're good up in what we're telling that server is that we're good up to 46721, sequence number 46721. What we're doing here is we're saying, hey, Mr. Server, I'm good up to the acknowledgement number that I'm telling you. What I'm missing though, or the next block of data that I received is between 59,861 and 61,321. So between the acknowledgement number I'm sending you and the left edge of what I'm advertising, that's the data that I'm missing. That's what I need you to retransmit. Okay, so this is where we see another packet come in from the server. We see another dupeback. But then we come down here to this window full. Now, keep in mind which direction Wireshark is flagging this on. Now, TCP window full. Let's talk about that for a minute. First of all, what is a TCP window? Basically, when we see it in terms of Wireshark, what we're talking about is the TCP Receive Window. Now, the Receive Window it's advertised in each packet. What that means is I'm telling my link partner how much data I can receive at once unacknowledged. It's basically the size of my receive buffer. So for example, if I can only receive 64K of data at once, if that's what's been allocated to my TCP connection, I'm going to advertise to you, if you're the server, hey, I can only receive 64K at once. Don't send me 65, 66, 70K worth of data because I don't have enough buffer space for it. But as you begin to stream data to me, I'm going to begin to acknowledge that data that you're sending. If that data ever gets stuck in my buffer, if the application isn't reaching in and scooping out, clearing out that buffer and processing that data up to the layer 7 application, well then that data that's sitting in that buffer reduces the amount of space that I have to receive more data. So if I have a 64K buffer and you send 10K and it gets stuck in that buffer, I'm going to reduce the amount I can receive, 54K. If you send another 10K, I'm going to say 44K and so on. The amount of size of my TCP receive window will get smaller. Now that TCP receive window, we'll come up here to our SYN, SYNAC, ACK, and our handshake. We can determine that window size based on our handshake. Now hopefully in your trace files you can capture these handshakes because there's a lot of really good data in there. So from the client to the server, let's come down to our TCP header. We're going to come down to window size value. We're advertising initially 8192. And if I expand out my TCP options, if I come down here, I'm applying a window scaling factor. Now what that means is it allows me to increase the amount of window size above 64K. Now this window size value, it's only a 2-byte value in the TCP header. That means it can only be 64K without help. Now what the window scale allows me to do is multiply that number that I'm advertising by a window scale factor, and then I'll receive an actual calculated window size, whatever that ends up being. Okay, so since we've captured this in the handshake, we can now see down in each one of the ACKs that come in from the client. I'm just going to select one, packet 66. This is where the server, it began to respond. We see our request here. The server begins to respond in this HTTP 200 OK. We see another packet, then we see an ACK from the client. So this ACK is ACKing the 2 packets above. If we come down here to our calculated window size, when we apply the window size value and then the multiplication factor, the calculated window size from the client end is 17,520. So in addition to acknowledging these 2 packets that were sent from the server, the client also says, hey, Mr. Server, you can only send me 17,520. That's what the size of my window is. So the server says, okay, let's go ahead and send 2 more packets. And if we take a look at the ACK from the client, calculated window size 17,520. So we can see that this continues and continues and continues. If we come down here, though, to that window full, what this means is that Wireshark has seen so much data in flight that the server has reached the maximum amount of data that it can send unacknowledged. So that server, by the amount that it has transmitted, has hit the window size by the amount of bytes that are in flight. That's why Wireshark is saying, hey, the window is full. So it's pretty common to see when we have TCP window full and then some packet loss. That's a common error set that we can see in Wireshark. The server, it sends out so much data that the client, that's all the client can receive at once, and it congests the network temporarily, causing packet loss. So a lot of times what I'll do is I'll look for packet drops between client and server, see if we have any duplex mismatches, any errors that would indicate that the network had dropped packets because it saw this microburst. Now, I'd like to show you another example of a trace file where we saw bad TCP, but it didn't necessarily indicate that there was a problem with the network itself. Okay, so I'm going to open up my trace files, and I'm going to bring this up. Okay, so right away, this trace file, we see some bad TCP, right? We see the black lines, ugly red. It's definitely indicating that we have some issues going on. Now, the symptom that this trace file was captured for, what we were troubleshooting, was client or an application that was performing slowly. Clients would click on a certain tab in their application, and they would sit there and watch a spinny wheel for several seconds, even over a minute, before we would see that page populate. All right, so let's go ahead and dig in and see what is really happening on the wire. Now, first of all, we can see that we have a good handshake. We have SYN, SYN-ACK, ACK. Now, right away between the client and server, I know we've got 97 milliseconds of round trip time. Now, sometimes people ask right away, is that bad? Well, if that server was 1 hop away, that'd be bad. If it was 2 hops away, I'd wonder, why do we have 97 milliseconds of latency between this client and server? It really depends. It depends on where this client is, where this server is. Do I go through a service provider that I don't control? There's several factors that I need to consider. But if I come down to the SYN-ACK, I can come down to the IP info, and I see that the time to live is 111. It's 111 hops. That's how many hops I have left. So I can guesstimate, I can take a pretty good swing that this packet has been routed 17 times. So now with that number in mind, I can come up to my 97, and I'm okay with that. I'm not super upset that I have 97 milliseconds. That's certainly not what the clients are punching their screens for just yet, or seeing those spinny wheels. So send synac ACK, and we see from the client, I'm just going to expand out my length here. This is a full-size packet, 1514, from the client to the server, and the client saying, hey, here's a get. This is a request coming from that client. This is a give me. Now, what it exactly is, I don't really care right now. This trace file has been sliced, so that data payload hasn't been captured, but I'm not too worried about that just yet. What I first want to figure out when I'm troubleshooting something like this is it a network problem or is it an application/server problem? So we see the request comes. Now this request was so big that it filled one packet, and we had to have another second packet from the client to the server just to carry the rest of the request. Maybe there was a cookie in there, maybe there was something that exceeded that one packet limitation. All right, so we have a 2-packet request. The server comes back with 106 millisecond response. So that tells me that those 2 packets made it to the server. The server's telling me, I got your request, hang on, I'm going to go to work. Then we see our ugly black lines. So if I click on that first packet, notice how long we waited before this packet was sent. Now the sender of this packet is the client. This is a packet with no payload. It's 60 bytes, or plus 4, the FCS on the end of the packet would have been 64, but this is a small packet. It's simply a TCP keep alive. We waited 45 full seconds. We didn't hear anything back from that application server. So what we're doing as a client is we're checking in. We're saying, hey, are you still there on the other side of the phone? Or have you hung up? Did you disappear? Did the client, or did the server die? Did the server's port disappear? Did something happen on the network between client and server that severed communication? What happened? So the client's saying, hey, are you still there? Server comes back 99 milliseconds later. I'm happy with that. That about matches my round trip time. 99 milliseconds later, server says, yep, I'm still here. Okay, shrug. We hear nothing else from that server till packet 9. Another 45 seconds later, client sends to server a TCP keep alive. Now what this is doing is, like the name implies, it's keeping the TCP connection alive. See, TCP wants to time out after a certain amount of inactivity. If one of these 2 sides is dead, if the service has gone, or the service has dropped, or some other network event has severed connection in this TCP channel, we want to shut this thing off. We want to open up that TCP resource to other things on each side. So here, that's why a TCP keep alive will keep that connection alive if we hear a TCP keep alive ACK, which in this case we are. So we send another keep alive. The server says, all right, yep, I'm still here. Let's keep this open. Server's still working on it. Don't hang up on me yet. Finally, packet 11 comes. This is 18 seconds after the final TCP keep alive ACK. 18.45 full seconds, and now this has measurable data in it. This is an HTTP 200 OK. This is the first packet of response from that server. After this, we're good. Like if we take a look at the delta times, I mean, these aren't blissfully fast, but in comparison with 108 seconds of delay, this is lightning fast. In fact, once we start to transmit data, let's go ahead and keep our minds on that 108. If we scroll down, all the rest of this data is coming in 109. I mean, we're doing okay, right? Then the next get happens down here. That's why we see that jump in time, that 4 milliseconds. Okay, so for the request above, we were sitting there waiting for the application to respond for 108 seconds. So there are times, by using bad TCP, if we see things like keep alives, and if we filter in on the TCP conversation that's generating them, It could be like in this case, the network itself was absolutely not to blame. The application was sitting there waiting for 108 seconds to respond. Now we might be thinking, well, what if that 108 seconds was simply taken up because the server let this packet go and it swam around on the network for 108 seconds? Now that is tremendously unlikely, or actually I should say impossible. There's no, I've heard someone say one time, there's no red carpet lounge where packets go to hang out on the network. They don't just enter a switch and say, I'll just chill here for a while. That's not what packets do. They go into a device, they get processed, they come out of that device. Especially when I look up here, 97 milliseconds, that's my benchmark network round trip time. So it's impossible that the network was just sitting there on this response. Okay, so the next thing that I want to do with a trace file like this is I've captured it here from the client side. We saw the requests go out, we saw the response come back 108 seconds later. The next thing that I want to do to further troubleshoot this is to move to the server side and run another capture. Hopefully we can reproduce the issue, or best case, we captured server side simultaneously while capturing client side. So then we can come and look and see what I want to know is what was that server doing for 108 full seconds? Was it looking at some backend system? Was it looking at an Oracle server? Was it looking at a SQL box that was taking a long period of time? So those are the kinds of questions that I have. So what Wireshark has helped us to see is that these delays have nothing to do with the network. Although we do see some bad TCP, what this does by starting at the transport layer, it allows us to look up at the application and immediately exonerate the network below. And that's our goal. Okay, up next we have another example. Let me open up the next trace file. So now we're going to take a look at an example of where TCP showed us something that wasn't necessarily a network issue, but we did see an issue with bad TCP. Now the basic, just to tee up the details here, what was happening is we were doing a backup. So just simply put, from a primary backup server to a destination backup server. And this backup was taking hours of time. In fact, the person that captured this, he would tell me that he would begin the backup after people went off shift at the end of the day, after 5 p.m. And he would run it, and the thing wouldn't even stop until the next business day when people started to come into work for the morning shift. So this backup was taking a long amount of time. Well, what he wanted to know right away is, Chris, what's the problem? Is it a network issue? Do I need to throw more bandwidth at this? Do I need to go from 1 gig to 10 gig? Do I need to go from 10 gig to 100 gig? What's going on here? Of course, because all the server and application people were telling him, hey, you've got network issues and your network's too slow to handle this backup. So right away, when we open up this trace file, if we come in, we can see our bad TCP button. Let's go ahead and click that. Right away, we can see window updates. Okay, now what a window update is, it's when the receiver of data, or whoever sent this packet, is telling us its window size has just increased. It's gone from one value to a new value. Now what I learned from this is that, first of all, I don't have any TCP retransmissions, do I? No retrans, no out of orders, no dupbacks. So right away, I'm not concerned about the network dropping traffic. In fact, right away from layer 1, 2, and 3, I'm good. I don't have any issues there, and I don't see anything that's really pertinent or things that I need to go digging around in those lower layers about. But what I do want to do is figure out where are the delays coming from. All right, so the next thing that I'm going to do after filtering on the conversation between client and server, which is what I've done here, I can see that the server that's sending the data, the 1514s, are coming from 192.168.1.1. They're going to 192.168.1.2. So .2 is the receiver, .1 is the sender. Now I've filtered on just this connection between these two, the primary server and the backup server. Now the next thing I'm going to do, that's important to do, first of all, because the next thing I'm going to do won't make sense unless you filter on that conversation. Okay, so the next thing I do is come up to delta. This is our delta time. This is our amount of time between packets. What I want to know is where are the delays? Where are things being held up? If I click on delta, it's going to show me the delays between packets that I see for this entire trace file. Now what I want to do is look for patterns. I want to see what side of this conversation are we waiting on here. Now most of the delays are coming from which side, dot 1 or dot 2? I can see that I do have an exceptional one, 60 milliseconds, that's coming from the server, but most of these delays are coming from dot 2. Now they range anywhere from 20 milliseconds, up here 17 milliseconds, I see 25, I see 32. If I scroll up a little farther, I can see dot 2 is even further responsible for more of these delays. So I can definitely see that I have periods of time where I'm waiting on dot 2 to respond. Now that's something that I want to be aware of. I also can see that some of those delays are coming from packets where I see window update. All right, this is all just note to self. Okay, so what I'm going to do is sort on number, and I'm going to go back to the top of my trace. And what I want to do is look for the first delay. So what I'm doing right here on the delta column, I'm going to go ahead and click down. It's going to show me coming up here real quick. Oops, there it just went by. There's my first delay. 19.8 milliseconds. So things were moving along just fine at less than 1 millisecond delays between packets. Things are sub-millisecond. Things are going on wire speed, transmitting data between one point to another. And here we come up on this screeching halt. Now 19 milliseconds doesn't sound like a lot of time, does it? But in context, it does. When everything else around this 19 milliseconds is sub-millisecond and things are just screaming fast, this 19 milliseconds looks like a complete roadblock. In fact, mentally, move this decimal point over. What if I had 71 milliseconds, 52 milliseconds? I know these aren't milliseconds, but just bear with me here. What if this was 71 milli, 52 milli, 122 milli, and then I see this big whopping 20 full seconds? That's basically what this is telling me. Everything else is screaming fast, you've got this delay. But what was it that was causing this delay? Now remember, this is coming from the client to the server. If I go up above that packet to one of the previous packets from the client, right now I'm only interested in packets coming from the client. The server, I'm not worried about him. He's not causing these delays. I want to take a look at the client itself. In fact, I'm going to come up here to display filter. I'm going to do ip.src for ip.source equals. I just want to filter on only the traffic that's coming in that was sourced from .2. Okay, so these are only my ACKs. These are not the packets coming from the server. Now also, in my TCP plane profile that I have here with Wireshark, another column that I added was window size. So what you can do on any packet, come down to your TCP window size, and it's best to do this for calculated window size. You can right click and you can say apply as column. What that does is it shows me, do I have a window size that's falling? Is this client that's receiving this traffic and acknowledging it becoming congested? And here I can see, sure enough, it is. This window size starts high, 65,535, 65,535, and then I can see right around here, it starts to bog down. This TCP buffer starts to fill. 64, 53, 38. It goes all the way down to 2299. After 2299, we wait. There's our 20 milliseconds. Then the client updates its window. It says, hey, I'm back up to full, or I'm not full, I'm empty. I'm back up to 65,535. Go ahead and resume. Start sending your traffic again. Now, if I pull off my filter, and we're sitting here at that 22.99. Check out what the server does. The server says, okay, great. Here's one more packet. You can fit one more full-size packet inside that window size, inside that buffer, which this is interesting. The window size doesn't go to 0. It goes down to 22.99. Now a 0 would absolutely tell me that I have a congested window on that receiver. But it doesn't go to 0. It just slows down the server. The server says, all right, here's one more packet, and then the server stops transmitting. The server can't send anything else until this window size gets cleared out. So it waits 20 milliseconds. The client sends to the server, hey, I'm back up to 65,535. The server takes off like clockwork. 1514, 1514, 1514. It just bursts a bunch of data out on the wire. Then the client begins to act. Okay, so we see this go on. If I scroll down, we're going to see another delay coming up here around. This is a good long burst here. Boom, 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 boom. And what I'm looking at is my delta time column right here. So this is where we see, so data is coming in, it's being acknowledged, data is coming in. Uh-oh, the window's falling. 6,487 bytes, 3567, 1459. This packet right here stops the server. The server can't send anymore. The data that's being sent in these packets, these 1514s, is 1460 bytes. So right now I'm telling him I've got 1 byte less than a full-size payload. So the server stops. Server says, okay, fine, I'll wait. We have our 14 millisecond delay, and then the server takes off again. Okay, so these little pauses, while they don't seem like much, notice how long we're transmitting. If I come back up to the top, and I'm going to look for that 19 millisecond delay. Sorry. Let's scroll up above here, and here's my 19 millisecond delay. What I want to see is how much time do we spend transmitting versus waiting. So if I right-click the packet just after that delay, the next one from the server, if I come to set unset time reference, or I could say Control T, either one, what that does is it resets my time column back to 0. So from 141, I want to time how long do we spend transmitting versus waiting. So I'm going to go over to, let's see, my next delay. If I take a look at the window size, you can see when the delay happens, because that window size number, right here, it's starting to fall. On my 60 byte axe, it's starting to fall. So let's go ahead and get down to where it goes down to 1459. There's our pause. So we spent 16 milliseconds transmitting and 14 milliseconds waiting. So just for this burst, half the time we spent transmitting versus waiting. So it bursts, waits, bursts, waits, bursts, waits. Now, later on in the trace file, this is just near the beginning of this transfer, this burst versus wait delay gets a lot worse. We're only sending just really small bursts of data, and that window is filling really quickly. So here I can see that there's several things at play here. First of all, the application on the client side is not clearing out the TCP window as fast as data is coming in. This 14 milliseconds is the amount of time that it takes layer 7 on the client to scoop out that data and open up the TCP window again. This is where we can see that there's that difference between layer 7 and layer 4. So that's one thing at play. The second thing at play is we're not using window scaling, so 64, 65, 535 is all that the server can put out there at once. Another thing that's going on here is we can see that this backup process is using a single thread. It's only using one TCP connection to move all of this data over, 13,782. Now, right there, when you do this type of analysis with a trace file, there's going to be some things that you can change and other things that you can't. Now, for me, I'm not an application coder. So the last thing that I want to do is get in there in the client and figure out where in the application code does it have the amount of time that it goes in and scoops out the TCP, or it processes the data up from layer 4. Not my job, not what I do the best at. I'm a packet and network person, so that side of the house is something that I try to leave alone. What we ended up doing to patch this while we got a hold of the vendor that does write that code is I went ahead and asked my friend that captured this. I said, hey, you know, is there any options on that receiver or on that backup process where you can use more than one TCP connection? Can you do TCP? It's called multi-threading or multi-connection transfer. And he looked, and sure enough, that was a checkbox that he could click on the backup process. So when he went ahead and checked it, and rather than sending all of this data over one TCP connection, what it did is it opened up 20 of them, or at the time I can't remember the exact number, but it used a lot more connections to send the data from one machine to the next. So rather than one TCP connection bogging down and causing all of this delay just because we have only one lane of travel, what he did is he just opened up the whole freeway. So now he's got like an 8-lane freeway where traffic can flow down instead of just one lane of travel. Now, while some of those connections continue to show this behavior, while one would get bogged down, the others would continue. So with 8 connections, only one would fill while the other 7 continued, and then another one would fill while the other 7 continued, and so on, while we're waiting for an actual response from the vendor. Okay, so I wanted to show this just to see how we could analyze TCP, analyze that transport layer, and quickly determine whether we had network problems, and we saw we didn't. We were able to see that this was an issue that was rooted in TCP window, and then we were able to make some tuning from there. So that brings us to the end of this session that was presented at SharkFest 2016. Hopefully this was helpful to you. I appreciate you stopping by my YouTube channel and taking a look at this video. If you have any questions for me, please feel free to contact me directly, chris@packetpioneer.com, or you can post a question down in the comments. Thanks again.